My name is Michael Bagley. I completed my PhD here under the supervision of Brent Edwards, and now I'm starting a postdoc with Walter Herzog this fall. So Olivia and I are co-moderating, organizing the seminar this year, and it's very nice to see everyone again. So it's very fun. So today we're very lucky. We have a special guest visiting. This is Eng Kuan Moo, who he technically didn't finish his PhD here, but he did spend most of his time here. He finished his PhD in Malaysia at University of Malaya. Yes. And then he spent, that was in 2014, and then he spent 6 years here as a postdoc from 2014 to 2020. So if you've been around that time at all, you would have noticed Eng Kuan is a constant present all day, all night, all weekend, anytime in the visiting student's office, even though, far from a visiting student. But I have nothing but great things to say about Eng Kuan because he helped create this amazing environment here for all the students. And we're so incredibly lucky that he's been around. So today, great thing about Eng Kuan too is we'll start a new faculty position at Carleton University in Ottawa in January. Aside from that, aside from work, he likes all of the standard outdoor activities that Calgary has to offer. And so he's probably very sad that he's had to leave Calgary and move to Ottawa, which is much flatter than Thankfully, there are some hills there, though. So, in his pastime, he likes mountain biking, hiking, rock climbing. You name it, he does it. So, I'll leave the floor to you.
Thank you very much, guys. I'm very excited about the nice things that you said about me. I had been lucky to have a chance to work in a human performance lab. It's good that we come back and see everybody and see familiar faces. What do I want to say? So today let's go straight to business. I'm going to talk about the research that I've done with one of Walter's students as well. So the title of this research topic is how collagen fibrous network determines the damaging effects of tissue cracks. So this is a knee joint, a simplified knee joint that you are looking at. See the top part is the femur, bottom part is the tibia. Simplify in the sense that the patella is removed and you can see the meniscus here. So the white spot here that you see, I think everyone in this room will recognize is the cartilage. The cartilage is tissue that is there to ensure the smooth joint movement and lubricate joints during the motions to prevent any pain, make sure that we can move around easily. So articular cartilage has primarily consists of 4 constituents. Collagen fibers. You can see this is a cartoon of the constituents of articular cartilage. The collagen fibers in banded strips. Then you have proteoglycans that looks like a bottle brush. And this side, the broad brush are able to trap the water within the tissue and gives this swelling behavior to the articular cartilage. And within the space is filled with interstitial fluid and ions. The most typically known ions are sodium ions and chloride ions. So to have these normal functions of articular cartilage, we need these tension-resistant collagen fibers and the swelling proteoglycans to give the articular cartilage its functions and properties that is required for the joint motion. So, unfortunately, things that are good in the body don't last forever. At one point, you are fortunate, there will be a disease development. in the knee joint. For example, knee osteoarthritis, which is a painful joint disease that would cause redness, swelling, and joint stiffness. Now, on the left here, you see is a healthy joint. This everybody wants it, and when you're born with this hopefully healthy knee joint. But then, as your knee joint starts to degrade over time, you have this on the left here, mild OA. When you have start to have some symptoms, you can see some redness in this knee joint, and then you further develop if no treatment is taken. The knee joint will further develop into moderate OA. You can see those bone spurs that comes out. People call it osteophytes. That will restrict the joint movement. You can imagine how painful it would be if you have stretches during that joint movement. And of course, if still nothing's no measures was taken, it will develop severe OA, which is you have surface erosions of cartilage. The joint surface is deprived of any lubricating surface. Now, I would like you to put your attention to this cartilage with a mild OA symptoms, and you can see on this redness part some cracks on the tissue surface, and this is the main topics that I will focus on for this research talk. The tissue cracks is caused by overloading or overuse. So overloading in the sense that there's an excessive magnitude or excessive rate of loading of the joint, and overuse. By overuse, I mean more like a fatigue failure due to a repetitive loading of low magnitude, and these loading conditions can cause tissue cracks. And if no measures was taken for the tissue cracks to treat the tissue cracks, because the cartilage is aneural, so meaning that it's deprived of any neurons, so you cannot sense damage to that tissue if there is any. So if no tissue, well, typically anyone wouldn't go to a doctor unless they have pain in their joints or whatever. So during this early stage of osteoarthritis with tissue cracks, most people cannot sense the pain and no treatments will be taken. And if you are unlucky, this tissue cracks can progress into puncture lesions, which means a bigger compromise of that particular surface. And then it will, if still nothing is taken, nothing is done, it will develop into osteoarthritis, as you see in the previous slides, the terrible images of the knee joints. The mechanism of joint disease development from cracks is unclear. So the primary questions that we have in Otis group is to understand how do these tissue structure and compositions affect the tissue deformations around the cracks, and how does this affect the development of osteoarthritis from these small tissue cracks. Now, the study model to tackle this problem, we need a model to investigate, and one of the available models is the cartilage of different ages. So cartilage, as it age from a fetal origins to maturity, the structure and compositions within the tissue will evolve with time. So for example, the collagen orientations for the immature tissue, they are typically surface parallel. For the mature cartilage, it has this bending of structures. I'll explain to you what it means. So on the right here, you see 3D images of the cartilage with the cells seen as a wider spots. So on the left here is a fetal cartilage. B here is a calf, a fetal calf, and the adult bone tissues. So the cell orientations depends on the collagen orientations locally. As you can see in the fetal and calf, most of the cells are with round shapes, like small dots. So meaning that the collagen fibers are, in this sense, surface parallel. They are aligned mainly parallel to the surface. Whereas in the adult cartilage, you can see that in the deep zones especially, so this is the surface, this is the type mark. So this is the deep zone cartilage, you can see the cells are aligned perpendicular to the articular surface. So Benninghoff structures is named as Benninghoff because Benninghoff in 1925 discussed about these specific unique structures of collagen fibers within cartilage. So you can see that on the left here is the type of arcade-like structures for the collagen fibers within articular cartilage across tissue depths. So this is the time mark, this is the articular surface. As it goes from the deep zones at the bone cartilage interface to the articular surface, go from a perpendicular to articular surface and then eventually parallel to the surface. So that's what we call arcade-like structure. So another difference between cartilage of different ages are in the collagen content. The immature cartilage typically has low content. This is mature cartilage, it's the higher content. So with that model, then we can look into the purpose of the study and to investigate the cartilage mechanics and crack deformations in immature and mature cartilage exposed to a full thickness tissue crack. Now, the second objective would be to determine the key factor lies in the structures and compositions that determines the mechanics of crack cartilage. So we hypothesized that the crack morphology and crack mechanics differ between the immature and mature cartilages. So to perform this kind of study, to answer the questions, we resort to experimental and finite element analysis methods. So for the experiments, we perform a two sequential indentation loading to pig cartilage, and then we apply the tissue crack artificially, full thickness tissue crack into the cartilage, and then we measure the crack morphology by polarized light microscopy, which can uniquely determine the local structures of the collagen of the cartilage, which means it's given by the collagen structure. So for the finite element analysis, we developed a fiber reinforced poro-viscoelastic swirling material model. It's a very long material type. I'll explain to you what it means later on. And then with this model, the good thing is that we replicate the complex mechanical properties of cartilage in the computer, and then we can apply and regenerate the loading scenarios that we perform in the experiments, and then see internally what happened to articular cartilage in terms of blood mechanics. So we can interrogate the effects of structures and compositions. So I will describe some steps for the experiments before I move on. So first thing first, we got some cartilage bone explants from the foreside knee joints. So we have two types of cartilage obtained from two types of animals. One is immature animals, which is about 6 months old, and then mature animals, which is about 3, so skeletally mature. Then the specimens are fixed in sample holders by dental cement, and then indented by a 2 mm diameter flat-ended indenter using a material testing system. So to answer these questions, we categorize the specimens into 4 groups based on the maturity and the integrity of the articular surface. We name it as matured intact, immature intact, matured crack, and immature crack. So the two sequential indentations is crucial here for us to understand what the mechanics, the effect on the cartilage mechanics caused by the tissue cracks. So the first indentations for all 4 groups, will indent the cartilage at this particular strain rate, loading rate, 16 micrometer per second, to the peak pressure, peak contact pressures of 8 megapascal, and then we hold the deformations at the fixed strength, stress relax for 20 minutes. And then we wait for 1 hour recovery of the same samples. We wait for 1 hour recovery and perform the second indentation test. So the intact group, which means that the surface of the cartilage are intact in pristine condition, we perform just like the first indentation test using the same parameters. For the crack group, before we perform the indentations, we introduce artificially full thickness tissue cracks using a material testing machine. The blade that we use is 0.75 millimeter wide, and then it will go all the way to the cartilage bone interface to create this full thickness tissue crack. And the cut was made perpendicular to the split line directions by a sharp blade. Then after we perform this, we form these tissue cracks artificially. We perform the same indentations as the first indentations using the same parameters. So at this stage, I would like to focus on split lines. What do I mean by split line? So as you can see, this is a patella of the joint. This is the tibial plateau of the harvested knee joint from the pigs. And what you see, the dots here, they are not just simply dots, but it's a dot that are aligned primarily to particular regions, depending on where you look at. So for example, should be very clear. It is oriented around horizontally. So those patterns represent the split lines. The split lines are created by puncture the particular surface by a sharp object, for example, like a sharp needle. Then if you dip the sharp needle into an ink before you puncture the cartilage, you can stain the punctured surface, and then it will give you this nice orientation. The split lines typically represents the predominant alignment of collagen fibers along one direction in the transverse planes for the surface zone cartilage. So notice that these split lines features arises mostly from the tissue near the surface, not the full thickness cartilage. So after performing this, let's go back to the experimental protocol. After performing all the indentation tests, we then chemically fix the cartilage in the indented form by ruthenium hexamine trichloride solutions. So this is crucial because otherwise the indented form of the cartilage would be lost. Then after that, we went through a standard histological processing and then unstain sections of 8 micrometer thickness is then visualized by the polarized light process. So here is the example of the histological slides. On the left, you see the immature cartilage, and on the right, you see the mature cartilage. You can see, like, I want to, you notice that it's a very colorful image, and the reason it is colorful is because of this color disc, which shows the orientations of the cartilage. So it has two meanings here. So the color tone and the color itself determines the orientations and the degree of alignment of the collagens at a particular material forms. For example, if you focus on the superficial zones of this cartilage, it is very bright and it's about yellow-green. And if you look at this, the color disc, it suggests that the orientation is about horizontal. And then the brighter it is, the higher the degree of alignment of the particular collagen fiber bundle. Okay, so immediately you can see that there's a huge difference in the orientations between the immature cartilage and mature cartilage. So we quantify the crack morphology. So that's the primary variable of interest. We quantified it by these parameters that we call crack width. The shortest distance between the opposite crack surfaces, and it is highlighted in red these figures. So, okay. So here's the results in a graph. So on the y-axis, you can see the crack widths from 0 to 0.12 millimeter. So a 0 crack width meaning that the crack is really close. So on the x-axis, it shows normalized tissue depths from 0 to 1. So 0 means this articular surface, and 1 is at the pipe mark. On the blue curve, it shows the mature unloaded conditions, and on the red curve, it shows immature unloaded tissue group. As you can see, when you introduce artificially a full thickness tissue crack, the mature cartilage has its crack open wider than the corresponding immature cartilage. So this is a crack width without any load. Now, if you look at the crack width under load, if you focus on the solid lines for the red and blue color, so the solid lines represents a mature compressed state, and the solid red line represents an immature compressed state. And if we focus on to go from unloaded to compressed state for a particular age group, and let's say we focus on a mature cartilage first, it goes from a wide open state into a state where it is open at the superficial area and then close near as it goes deeper into the tissue. Whereas in the red cartilage, we focus on the dotted red lines, which is in unloaded conditions, and the solid red lines represents the compressed state. You can see that the crack, rather than getting smaller like mature cartilage, it becomes wider, especially if you go into the middle and deep zones cartilage. So this arrow indicates the directions of these deformations goes as the indentation is applied. Now, the crack morphology, you have just seen. How does it translate to the mechanical properties of the cartilage? So we look at first the instantaneous modulus. Instantaneous modulus is measured during the loading of the articular cartilage. So on the y-axis, you see the instantaneous modulus from 0 to 30 megapascal, and you have 4 groups here: mature intake, immature intake, mature crack, and immature crack, represented by blue, green, yellow, and red colors. So you can see instantaneous modulus of immature intake cartilage. If you focus on that, they are a little bit higher than, statistically higher than the mature. So pay attention to that. All of these 4 groups, they are in intact conditions in the first indentations. Now, during the second indentations, the things that changes is the crack cartilage, because at this point, then the artificial full-thickness tissue cracks was introduced into the tissue. Okay, and then we see those are the absolute value represented on the y-axis. For the changes in the second indentation relative to the first, we decided to present it in the form of a percentage change, right, rather than this absolute value. So from 0 to minus 30, minus 30%. So for the mature intact and immature intact cartilage, following the second indentations, the changes to the instantaneous modulus was minimal, and they are not significantly different from 0. Whereas for the mature cartilage and immature cartilage, with the introductions of the artificial crack, the mature cartilage, both of them, and immature cartilage have a substantial decrease of the instantaneous modulus. And in the immature crack group, especially, it has a increase. The reductions of this instantaneous modulus is high compared to the one from the mature crack group. For the relaxation time, so because we apply a fixed load and then hold the tissue strengths at a fixed nominal strengths for a stress relaxation test, so we will quantify how fast the tissue relaxes over time. So it's quantified as a relaxation time. It's the second TR. So again, we use the same model of presentations. The first indentation present the absolute value, and you can see that they are not mostly not significantly different between each other for the four groups. But during the second indentations, after the introduction of the crack, the matured crack group did not experience too much of a decrease of the relaxation time. It stays within the 5% from the original first indentation relaxation time. For the immature crack cartilage, the relaxation happens faster. So it is presented here as a decrease in that relaxation time, meaning that it relaxes faster. So, to summarize, when there is a tissue crack, in the experiments, we see that morphologically, under loading, the mature cartilage has the crack open in the superficial tissues, nearly closed in the middle and the deep tissues. The immature cartilage opens also in the superficial tissues, narrow in the upper middle zones, but then widen into a convex shape in middle and deep zone. So there was morphological effect. Functionally, the immature tissues had larger reductions of instantaneous stiffness and stress relaxed faster than the mature tissue. Okay, then the next step is like we want to understand what other factors determining this effect of crack. So some of the candidates that play a role are listed here. For example, the compositions. You have the Collagen content, collagen content. It will vary across the tissue depths. The structure as well, the fiber orientations, and the degree of alignment of the fibers locally also plays a role. So if I ask you that question, is how are you going to tackle this problem? Because experimentally, it's possible for you to test the mechanical effect of individual components, right? So the challenge will be to test the mechanical significance of each factor. So how do we do that? For that reason, we built a finite element model using this material model. So fiber reinforced meaning that we introduce fiber meshes within the material model. Viscoelastic swelling material. Or swelling means that it will swell, like the effect that is given by the presence of perfect lichens, side chains. As you see, like earlier in the slides, the brush-like, photo brush-like structures. And the viscoelastic is more like a type of elastic behavior of a material. So this is the geometry of a tissue model. The head is a half cylinder. It has a crack with a wedge shape in the middle. The length of the wedge crack is 1 millimeter. The width of it is 0.1 millimeter. The middle hemicircle here represents the area where the indentations occur. So the plane highlighted in yellow here is a plane of symmetry. So we don't model the entire cylinder to save the computational time. So importantly, I want to put your attention to this inset here. So this figure describes the statistical distributions of fiber orientations. So I wouldn't go into too much details, but conceptually, we have this fiber locally oriented in a certain directions defined by theta and phi, which is a spherical coordinate, and we represent it with a unit vector n. So that unit vector n can be expressed in terms of the two parameters theta and phi in the spherical coordinate system. E1, E2, and E3, right? And then these fibers are modeled as transverse isotropic material. Isotropic in the sense that it is relative to this polar axis k, which coincides with the axial directions of the tissue. Then the important things that I would like to remember is the probability distribution function used to describe the orientations of collagen fibers at a particular material point. Now, because of the split line directions and because of the Benioff arc-like structures, we choose to use these probability distribution functions because the collagen fibers are not typically not acting alone, but they're forming bundles, and then there's a certain degree of dispersions at each point of the material. So we use these bivariate von Mises distributions to describe these probability distribution functions for the collagen fibers. So in short, it's like how likely you are to find a fiber or in the, let's say, in the vertical directions with using these distribution functions. We'll tell you, or later on I will show a graphical illustrations of these distributions. So there's a complex formula, but two parameters that are important to control perform this study is the A and B, and they are termed as concentration parameters. And they are called axial and transverse concentration parameters. The axial parameters, it control the density, probability density functions across the depth. The shape of it depends on the B parameters. So for example, if you have a B parameters, so B parameters is shown on the axis on the left graph here, and on the right graph here, we show the value of the A parameters. It's the functions of tissue depth C. So let's say if you focus on the conditions where the B parameters has 0 value and A parameters 0 value, let's disregard the A parameters for the time being. You will have a completely isotropic collagen fiber distributions. And as the B value increases to positive values, you will have an orientation that align primarily along the polar axis. And then if you have the B value has stays in negative values, you have a isotropic, transverse isotropy relative to the polar axis. Now the polar axis coincides with the axial directions, which is the vertical directions. So for the transverse concentration parameters A, it is used to deviate this transverse isotropy within the plane. Right? So if we don't have this A here, this will be a disk. By introducing these parameters, we allow the disk to form horizontally lying orientations as shown in here. So that can be used to capture the effect of split lines, as I showed earlier in the slides. Okay, so using this, by controlling the parameters of B and A, we can recreate the collagen orientations across tissue depths to be either surface parallel, which is the features seen in the immature cartilage tissue, and also arc-like Benioff structures seen in the mature cartilage tissue. So in this particular case, if we follow these parameters as a function of tissue depths, you can create these arc-like structures because it goes from surface parallel to random and then to primarily commit with the articulate settings. Okay, so next thing is the depth-dependent cartilage compositions. We adopted these values from the literatures. Long story short, we can just follow the curve for the mature cartilage in red circle. It's a mature cartilage porcine collagens. So it increases from the articular surface to the deep tissues. For the immature cartilage, it has a lower quantity. For the proteoglycan content, which is on the secondary axis, y-axis, the literature found that the proteoglycan content was similar between immature and mature cartilage. So we decided to use the same values for the proteoglycan contents across tissue depths. So those are all material inputs for the finite element model. Now, to see the results, first thing first, we want to see how well these finite element model are able to predict reality. So we want to look at the predicted correctly in terms of morphology. Right. So on the left here, you see On the y-axis, it shows the tissue depth, at the top is the surface, at the bottom is type mark. And then on the x-axis, it shows the crack width in millimeter. The 0 crack width suggests that the crack width is fully closed, 0.1 is fully open. For the immature cartilage under compressed condition, with collagen orientations only, we have a crack that is open. Mainly, for the immature cartilage, it shows that it's open in the superficial zone and slowly close in the middle and then completely close in the deep zone cartilage. So to go back to this initial questions of which factors affect the effect of tissue cracks. So we have compositions in terms of proteoglycan content, collagen content, we have structures in terms of collagen orientation, and the degree of alignment of the collagen fibers. Right? So the way we investigate the problem is first introduce this collagen orientations effect only. So the rest are all isotropic homogeneous. And then secondly, we introduce the complexity, we increase the complexity of the model by introducing the collagen content as a function of tissue depth into it, and then we show the graph later, and then collagen orientations with the fixed charge density, and CD means fixed charge density is a surrogate measures for the proteoglycan content. And then at the end of the day, we include everything into a complete model. So as you can see, if the collagen content and the proteoglycan content plays a huge role, the shape of this crack width, predicted crack width, should be very different. Right? So let's see for the immature cartilage. As we increase the complexity of the model, the crack width stays almost similar as the one with only the collagen orientation effects. Same thing for mature cartilage. So with that, we conclude that this effect comes primarily from the collagen orientation effect, rather than the collagen content. So to show you in graph, on the top here, top left here is a mature cartilage. The blue dots indicates articular surface, and the green arrow shows the type mark. It has open crack in the superficial tissue area, and then deep zones are completely closed. Whereas for the immature cartilage, it is open across the tissue depths. Now we go back to this histological histomorphometric findings. It shows quite similar between the empty model and the reality. So that we are very happy about. Now we are happy about the finite element model. So we try to look into the parameters or the output from that model to understand what is the effect of these fiber orientations on the crack tissue mechanics. So what is the real impact of having a different orientations within cartilage of different ages? So we first look at on the left graph here, you see the peak contact pressures, which means the pressures that joint experience as you apply load to it. And then on the right here is a fluid pressures, which is a harder parameters to measure experimentally, right? As you can see, for the intact cartilage, with arcade-like structures, right? We focus on the red bar here. You have contact pressure about 3 megapascal. The fluid pressure developed is also about 3 megapascal. So almost the entire load was borne by the development of fluid pressures during the loading of cartilage when the tissue are intact and healthy. Now, if you focus then on this with a crack model, right? Peak contact pressures are relatively like almost the same, right? About 4 megapascal. But the development of the fluid pressure is extremely low. It drops to about 1 megapascal. So this is for the model with arcade-like Benningham structures, which is a collagen fiber orientations in the mature cartilage. We go to a surface parallel orientations, which represents the orientations in the immature cartilage. the scenario is even worse. The fluid pressures drop to almost zero for that case, meaning that during the presence of a tissue crack or a cartilage with the collagen orientations similar to a surface parallel orientations across tissue depths, the development of fluid pressures during the compressions of the cartilage is very minimal. But the load has to be taken somewhere. So the load sharing between the fluid phase and the solid phase are significantly altered, and they are all going to the solid phase. And previous studies has found that if you apply an increased load to the collagen fibers, then the chances of having the collagen fibers fail is much higher compared to intact conditions where you barely stretch or deform the collagen fibers, because most of the loads are borne by the fluid pressures. So to summarize, the key to crack morphology we found in the studies using experiments and finite element methods lies on the collagen fibers structures. To draw you a cartoon, if you have a collagen fibers that align primarily parallel to the articular surface, you exert this pulling effect, and then at the end of the deformations, the crack will open wider. Whereas if you have a crack that the fibers that align perpendicular to the articular surface, there will be no resistance to these deformations, inward deformations, and then you will see a narrower crack at the deformation state. So the mechanical implication of varying deformed crack morphologies lies in the fact that if you have an open crack, you will experience fluid loss and then a negligible buildup of fluid pressures. But if the crack narrows or closed, that allows the preservation of the fluid pressures for long period. So that's it. The studies are published in those two articles. If you are interested, I would like to thank my co-authors, Otis Group and Rami's Group, and then the funding resources like the fellowship and Academy of Finland, research chairs, and so thank you very much.
Right. So we'll take questions at this time from anyone. If anyone has anything to start. Yes.
When you did your the model and you did the crack and intact, did you do the crack with the loading also to see whether the collagen fibers can explain the behavior with the loading?
The crack tissue with the loading?
Yeah.
Yeah, all of them are derived from the loaded condition.
Oh, both of them loaded conditions.
Yes.
Okay, I see. The other thing that I had is about the fluid and the fact that the behavior of the cartilage should be explained by the collagen, but the fluid has a very strong relationship with the proteoglycan.
Yes.
Like being charged, and then it might attack, or like so how does it? Yeah, does it make sense that it only depends on the collagen fibers without any role for the proteoglycan?
Yeah. So
Especially because it depends, like the behavior depends mostly on the fluid
yes.
going out of the cartilage.
Yeah. So I understand. So that's you're talking more on the details of how to represent the proteoglycans in terms of the mechanical effect. So for the model, if the fixed stress or proteoglycan effect is not considered, we'll model it as no swelling. The model is no swelling, so it's purely mechanical. No. It's a biphasic material, but the swelling is negligible. So it's neglected. I'm not sure if that makes sense, because the final outcome will be the same. No, because the osmotic pressures that is given by the presence of the pressure will eventually translate into the compressive stiffness. So whether or not you consider that, it doesn't really matter in terms of the overall mechanical output. So that's why if we don't consider that dependent distributions of the fixed stretch density, we did not include into the model. Right? And then when we include it, the changes towards the crack width is very minimal. It's shown in the graph.
Can I ask a follow-up? So your proteoglycan then is modeled isotropically,
Yes.
and it doesn't take on orientation when you load.
It only depends on the volume change. Yes.
Am I remembering right? You showed a picture of your model predicted cracks versus the ones you measured. Am I remembering right that in the intact one, the crack started inside of the material, but on the picture, the crack was from the surface end?
Which one?
It was a few slides ago. It's the one where you were showing your the crack from your finite results versus the picture. Yeah. Yeah. So so you can see kind of how there, like your model predicted on the top one, the crack was started inside, and then your histology showed the crack was a surface crack. Did you explore that, like the reason for that difference at all?
Sorry. So this is a 3D image.
Oh,
Is that
I'm looking down at it.
So that's why I point of arrow here. So this is the articular surface, and this is the out of plane view.
Okay, I'm sorry that
Yeah,
that's why I got confused.
I understand the confusion.
This question for the doctor. But so your distribution functions that you use to like quantify orientation and distribution of collagen fibers, do you think that or do you know if people have used those to quantify like orientations in muscle fibers, or if there would be potential application?
Oh yeah, absolutely. There's potential applications in muscle mechanics, but I'm not aware.
No.
This was really good. Just curious, like how I think about in the human scenario, and I have no expertise on this, but I often hear that some of these occurrences that as we age, they're sort of like wrinkles or, gray hair. It's things that happen biologically and that they're natural, I suppose. In this model, when you look at a 3-year-old joint, how close is that joint to, let's say, the age that humans might be when they start to really suffer from this disease? Is a 3-year-old porcine joint?
Was it 3-year-old?
Wasn't that what you're like in your study? The mature were 3 years old, right?
3 years old, yes.
Yeah,
yes.
but how does that relate to a human? Like, would that be like?
You mean the translations of 3-year-old to a human age?
Yeah, I'm just curious. Yeah.
I would say like a healthy adult like us, like right now, not age.
And so if you were able to get an older,
That may be different.
yeah,
Because an age cartilage, you typically have an increased cross-link density. So cross-link between the collagen fibers,
yeah,
and making the collagen fibers stiffer.
yeah,
That is not good because the material becomes brittle.
right.
And it's less likely to absorb the shock applied to the knee joint or hip joint, for example. Yeah, so that shock would be translated more to the bone and offers less protections. That's what I understand.
And is there any reason why you wouldn't have or do you plan to maybe do a future study where you look at an older?
Absolutely,
Yeah.
absolutely. As long as I have access to the specimens, human or structural, I'm happy.
And sorry, last little question: How do you think it would be different if you did have that third group in this study? What would you have expected to see?
I would expect it to be very similar to the adult cartilage, but then if you are asking only about the age cartilage without osteoarthritis, then it will be very similar to this one. But if it's diseased, then you may have surface erosions, you have fibrillations here, then circumstances become more complex. It's a good thing to think about for the future studies.
So were those explants from all condos to your project like this?
For the experiments, it's from patella, femoral condyle, and tibial condyle. So it's performed by Yasir Asafa.
Like, have you also explored like taking explants from different sites across the?
Yeah, they are taken from across different sites. So we tried to do a statistical comparison, and we did not find differences, at least in the mechanics. But the limited number of specimens may be the cause of that. So they're not sure. But definitely a systematic analysis, you get a lot of sample size for a single specific region, so it will be very helpful.
In your FDA model, you have considered the same boundary condition between the cartilage and bone for immature and mature.
Yes.
Okay, can you explain a bit about this assumption? Because I think that the problem can be related to different properties of bone at the interface of cartilage and bone. And the behavior you have seen can be likely related to this bone, that we have quite different boundary condition.
Yeah.
And you've assumed the same boundary condition there,
Yeah.
right?
So by boundary condition, you mean the fixed boundary conditions. Right now, I fix the end. So this is the artifacts. You see that the cracks are closed. The reason being, I fix the boundary conditions at the time mark. This is the artifact from the model. But yes.
Can I just ask a quick follow-up question, because I was surprised that, as you showed there, in the final element model, your split, your crack is always fully open at the boundary, and I would have expected it to be fully closed in the experiment.
In the experiments.
Yeah, because you go down, but then at the boundary, I thought it would be fixed, and therefore it would not go apart.
Yes.
So I was wondering why you actually had it modeled fully open, if there was because to me that seems intuitively exactly the opposite of what I would have done.
Yeah. So as to facilitate the calculations and the generations of the model, I had to do this. The geometry of the model. As you can see here, it started with a wedge shape. So whereas in the experiments, we have this sharp blade that goes into the to the time mark and stop. So it's more like introducing a crack, a slice, cut, sharp cut. Where this one, you take off a small piece.
Oh, you take out a piece of, okay,
Yes.
and that's why you have to do that at the bottom there.
Yeah.
Okay.
To facilitate this study.
Yeah.
To go back to that questions, by boundary condition, do you mean the fixed boundary conditions at the bottom?
Yeah, but I think that properties would be very much different in two different cases because of having different material properties at the interface of cartilage and bone in immature and mature cases. So the problem can be caused by this. One reason can be different properties.
Yeah. So one way to account for that would be to include the calcified cartilage layer, right? This is what we're trying to say. Calcified cartilage and then the subchondral bone. And it is true that the material properties of the calcified cartilage in immature cartilage versus mature cartilage are quite different. But still, the stiffness of the calcified cartilage, whether or not it is immature or mature cartilage, they are far higher than the cartilage. So it could be potentially different if we implement the calcified cartilage in this one.
I think the behavior you have seen can be related to the quite different anchorage mechanism between the collagen fibers in the deep zone of mature and immature cases. The anchorage mechanism.
Yeah.
Because the fibers there in the mature case are like nails penetrated into a stiff bone, whereas in the case of immature, you don't have this kind of story. So if you apply load perpendicular to the direction of fibers in the mature case, you do expect that you shouldn't see separation in that region. Whereas in the case of immature, based on the physics of the problem, we expect that we have to see the maximum separation at the interface of cartilage and bone, because the anchorage there is not as strong as the mature case.
Yeah, yeah. But the anchorage of the fibers to the calcified cartilage and to the subchondral bone is not of our interest at the moment. And like I explained earlier, this model was created with a wedge-shaped crack with a small piece of tissue taken out, are quite different from what the experiments, because the experiments is more like a sharp cut without taking any piece of cartilage out of it. And what we are interested in is just the deformations around this crack. We have this open crack with a different orientations. How we
So just to follow up, is there any indication that cartilage cracks propagate into the calcified cartilage or into the bone?
Indication. They are both. So the cracks can go horizontally oriented, or obliquely oriented, or all the way to the pixels. It really depends on the.
No, I meant, is there any indication for cartilage cracks to propagate into the calcified cartilage or into the bone?
I don't know.
Because I would think not. I would think the boundary is so much stronger, so that really the argument there probably becomes irrelevant, because I don't think you would see any propagation. It just stopped dead, because that boundary to me would seem to be so much stronger than anything else that you have in the cartilage.
So there's a research group in New Zealand. His name is Neil Brown. So what he did is, previously he tried to investigate the adhesion strength between the bone and cartilage. So the way he measured it is had this pendulum, large pendulum, swing down to the cartilage, like swing down like this, and hit at this exactly at that interface, and see how much the strength between the two, like cartilage and the bone. So he's the one who measured a lot of the cartilage bone interface properties. Like I said, I don't think this applies to the particular cartilage or morphology.
I just have a few comments. You see cracks in calcified cartilage all the time, but I've never seen cartilage cracks going to calcified cartilage. That makes sense.
So you see
cracks in calcified cartilage,
but not in the cartilage.
never seen a crack that spans into articular cartilage.
So the cracks develop internally.
You could say that, I guess. I mean, the cracks develop in either the subchondral bone or the crack, or in the calcified cartilage.
So if I can summarize, so typically we'll see cracks on the articular surface, or internally at the calcified cartilage or subchondral bone. But
yeah,
no,
I'm just saying, like, observationally, I've never seen a crack that, to get at Walter's question, I've never seen a crack that looks like it propagated from the articular cartilage to the calcified cartilage. The other thing that I wanted to comment on, which I just love, I asked Salvatore once, I'm like, why does cartilage fibers in adult cartilage, why is it vertical? I thought he was going to give me like this really like interesting explanation. And he goes, because it has to be anchored into the calcified cartilage. And I just thought, oh, that was really easy. That was so. I'm just wondering, do you think that the cartilage orientation is some kind of structure-function relationship? It's oriented in a way that prevents maybe cracks from opening up, or maybe from carrying too much of a solid phase versus, well, I'll stop there, versus carrying too much in the solid phase. Or do you think it's just something literally as simple as that? They're anchored, and so they have to be vertical.
Well, I'm not sure if it applies to cartilage of all ages. And in here, you see that the cartilage fiber is mostly parallel to the particular surface. So I don't think people have this. Yeah.
Which then would be interesting to see if indeed the attachment of the cartilage to the bone in the immature animals where it's parallel would not be as great. And so if Neil Broom did his experiments, would he actually just tear away the cartilage if he did it was immature?
But he actually measured this adhesion strength to be about 3 gigapascal. This is very tremendous strength between the two singular material.
Thank you, Kwan, for your presentation. When I saw your animation, I just wondering about the progression of the crack.
Mm-hmm.
So your model could be predict or maybe test the other direction, the load in different directions that create different path of the cracks, for example. And it depends on the tension of the collagen as well as you explained in your figures.
So you mean like to have a different directions of the load?
Yeah, for example, horizontal, that
like shear strength, the shear load. Yes, it could be done, but it's not done because of the technical difficulties. To perform these experiments, people from Larry Lawrence Bonassa from somewhere in Massachusetts. Yeah. So his group performed this kind of shear loading experiments. I'm not sure if you look into the crack found, but I think it's, it takes time for these kind of experiments to develop over time. So for the time being, he's looking at the tissue engineered cartilage or intact cartilage shear mechanical problems. Then to some basis adhere to the balance and then apply the sideway load. And now in the finite element model, of course, we can do it because we just implement the boundary condition and see how it goes. The problem is if you don't have experimental verification, it's hard to convince people that, oh, this is actually real. So let's say we find something interesting, and then we put it out to the public, and the public will say, well, it's not true, I don't believe it, because you don't have experimental verification. So the thing that we can conclude these things, there's some insights into this is because we happen to find that, oh, the finite element predictions match with the histological finding. So that gives us the courage to say, oh, maybe this is actually what is happening within a tissue, but no one can actually claim that it's the case. It is the background of all of it.
While we're on the topic of the model, the correspondence between the experimental crack displacement and the model crack displacement is very impressive. So I'm just wondering, did you have to fiddle with the modulus? I mean, did you take the modulus that you got from the indentation in the experiment and you used that and the results were that good, or were you playing around with stuff?
Yeah, I play around with the
All right. But it's really about the relative change. And my last
I
question.
can add to that.
Yeah.
That thing. So recently, I did Rami's group because Rami is strong in simulation and element analysis. So and then his group also have access to human cartilage with different osteoarthritis stage. So that measures like histologically collagen collagen orientations across tissue depths. So I saw that the data was there, so I decided to implement it into a model. So that was obtained completely from the compositions properties, measures from the experiments, and then we somehow derived the material properties for the collagen fibers. So here, the collagen fibers are the one that is mainly gas focus. Right? It's used as an 8 megapascal, but we all know that it's higher than that. So in that particular study, when we use composition and structures details from the experiments and feed into the model, and the value that comes out of it shows that the collagen fiber modulus range between 100 to 800 megapascal, which is reasonable because others have done individual collagen fiber tensile stretch and found similar values sometimes. So if I implement this to here, then probably we will have different results.
The last maybe question that I have is, I'm sure it has no answer, but I want to get your thoughts on it. So one way to think of it is that you have a crack and it's bad because you start carrying more load on the solid face of the cartilage. Another way to think about it is that it serves as a conduit for debris or catabolic protein enzymes to come get into the articular cartilage itself. So I'm just wondering, do you have, which do you think is more important? Is it the mechanics, or, for lack of a better term, the biology that makes these cracks that big?
Well, that's very good comments, good questions. So during the review process, the reviewer also asked the same question, similar questions. What's the biology? I'm sure it's not you. So obviously the crack, the formations of tissue cracks cannot be good. It's a compromise of the material. It cannot be good. But the effect of the crack over time is a different story. Right? It depends on the health state of the material of the biological tissue. So I have to give these limitations of the study. Of this study is that we only look into the mechanical aspect of the particular cartilage, but biologically, the immature versus mature cartilage are very different. So, for example, the cell density, the one that I show you in the early slides, in the second and third slides, you can see that. Yeah, you can see that the cell density here is much denser than this one. So the cells in cartilage, chondrocytes, the higher number you have within the tissue, the more workforce for you to repair it if there's any issue. So in that sense, the repair potentials for young cartilage or immature cartilage is supposed to be higher. And then also people look into the biosynthesis rate of the cells obtained from immature cartilage versus adult cartilage. They found that for the immature chondrocytes, they are 2 times as biosynthetically active compared to the adult chondrocytes. So that matters. So, like you say, we never know. Maybe even though mechanically speaking, the immature cartilage crack doesn't close, but then it stimulate the cells within it to perform some repair process. That
Maybe I shouldn't have used the term biology because I'm not really curious about the difference between immature and mature. I'm more in terms of disease progression. Is it the change in mechanics associated with the crack that leads to worse osteoarthritis, or is it just simply a conduit now for debris and other catabolic processes to get inside the articular cartilage?
to get inside, if you think about things that get inside, you can also think about things that get outside. right? So the proteoglycans are enmeshed within the collagen fibrous membrane. So if you don't have a breach to the surface or the articular cartilage, then nothing will flow out. But if you have that tissue cracks, that proteoglycan may flow out as well at the same time. So which happen faster, the thing that go in and the thing that go out?
Were the immature and the mature cartilages of equal thickness,
No, they're not.
but you applied a strain rate that was the same, absolute strain rate?
Yeah.
So do you think it matters that your relative strain rate was not the same?
It does, but we have to fix certain parameters for the two material types. So that's why I think the rationale for choosing not a conventional stress relaxation test by controlling the displacements, rather we apply a fixed loading rate and then aim for the peak contact pressure, which is about 8 pascal. And then depending on the stiffness of the cartilage, as you can see, the immature cartilage is stiffer than mature cartilage. So the deformation should roughly even out, even though the thickness. And indeed, the amount of the deformations are not like 10%, I would say.
And I assume the fluid results, how much is borne by fluid and how much is borne by the matrix, that was based on the 16 microns per second indentation. Is that correct? Or is that?
That was based on the finite element model.
But,
they are all the same loading rates.
Yeah, but again, the fluid pressure that you get at the end of the day, the distribution, that would depend crucially, presumably, on what rate you're choosing.
Yes, you're right. So the faster you apply the load, because the fluid pressure that I'm talking about is the transverse space, right? If you hold it for a long time, then the fluid pressure will go down. Yes. So,
but you think the trend between the immature and mature would stay the same? It will not all of a sudden conceptually go different if all of a sudden, that you have a switch in the behavior depending on the rate that you apply it.
There's this uncertainty here. I cannot say for sure that the trend stays.
And then just the last comment, just talking earlier, to Baba today in our meeting, and she looks at dynamic cell deformations in articular cartilage and finds that they are completely different from all the static loading that Gilak and other people have done. And your deformation, of course, the experimental one that was done after 20 minutes, in static situation. Do you think that the crack, when you walk and you apply a load for half a second every step, so you load it cyclically once a second for half a second, do you think the crack behavior would be similar or completely different than what you find at that steady state, fluid is gone, everything's carried by the matrix kind of situation?
So at the transient phase, I would expect the deformations to be less because the tissue will perform more elastically. And then because of part of the load spawned by the fluid pressure, the solid will not have to deform that much. Right? If the model is that the model response that you see here right now is at the peak rate, not at the end of the stress sessions.
Oh, so it's kind of like
you will become
so it's
wide.
right at the end of the loading phase.
Yeah.
Oh, okay. So is that fair then to compare right at the end of the loading phase when you still have substantial fluid pressure compared to, what did Yassir do? 20 minutes or 30 minutes? 20 minute relaxation before it compressed and essentially fluid pressure is all gone. And
it's not entirely fair, but
you think it's valid? It's the same. It's similar.
The trend will be similar.
Okay.
Yeah. One will be smaller than the other. They will but the magnitude of the
But conceptual behavior you would expect it to be similar.
it's very different between when you consider tissue and cells, because they are such different material. Cells are a lot free in it, and the impermeable membranes, or almost impermeable membranes. The permeability of the cell membrane is so low compared to the permeability around the peripheral matrix.
And
I expect that
and it's presumably regulatable by the cell. You know, like you and Rami have shown is the osmotic experiments, you know, that there is an active, potentially regulating membrane that allows things in or out and pumps things in or out.
Yeah.
To kind of maintain a preferred shape and size. And
Have you considered the anisotropy in your FE model between the difference between mature and immature cases?
Are they
Anisotropy, yeah.
Yeah, all the models there are anisotropic because of the inclusions of the collagen fibers.
And anisotropy would be different in different regions, right? Superficial.
Anisotropy? Yeah, it depends on the collagen fibers.
Okay.
Yeah, if I use the immature conditions, then it will be similar across tissue depths. But if I use the mature cartilage, it will be different depending on where you are at the depth position.
So Brent kind of asked the question that I was wondering for a while, but I still have a follow-up. Is the orientation in the cartilage dependent on which joint it is, or is it random between different people? Just knowing not much about cartilage. That's
Yeah. That's a good question. I don't think it is the same, not even within the knee joint, right? Depending on where you go within the knee joint, because in the knee joints you have a habitual loading area versus a non-habitual loading area. So that's why when you are injured, you change your gait, the loading point change, you will go from habitual versus non-habitual, then you really cause damage to the cartilage. So I will expect the orientations of the collagen fibers to be different, but in general, it has these arcade-like structures. So maybe the thickness of these superficial zones will be slightly different, but in general, they will be similar.
So a follow-up to that, when the habitual path or movement changes, can the orientation of the structure change over time?
I believe so because but it will go very slowly because the adult cartilage has a very low density of cells, so the remodeling process will be low because you have less manpower compared to immature cartilage. You know, you have lots of more power in cells.
So one last question
Yeah,
on that.
absolutely.
So depending on like individuals and how the structure is in different people, does that make someone more susceptible to developing knee OA, or like can someone train or change their movement pattern and change this to be less susceptible to knee OA over time, or?
Well, if you are talking about healthy persons, to identify who is more susceptible, it's almost impossible because you require the person to do some scannings, right? Like to build this patient-specific model, which is a strength of Rami's group. But if you have starting to develop symptoms, then from there you change the patterns, then yeah, then I can see that happening. But still, it requires a lot of efforts.
you know, Eng Kuan, this is completely unscientific. But sometimes I walk over to McEwen Hall and there will be a young student walking in front of me. And I'm going, that person is going to have OA. just by the way they move.
Yeah.
And I sometimes wonder, you know, if I say yes, yes, no, 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 yes, I sometimes wonder, you know, I would like to look at that 40 years later and see if I'm actually correct. But there's people that move in a way where you go, they must get OA.
Yeah. I mean, or they will have joint pain, maybe not to the extent of OA, but joint pain definitely.
Anyway, it's very unscientific.
All right. All right. So let's thank Eng Kuan again.